Thank you for being here, listening to a mathematician. So it's going to be a math talk. And I will start with some motivation. The idea is not to motivate you in studying tensor network because you are more motivated than I do, probably. but to study the dimension of tensor networks. So the title is Defectiveness. Defectiveness has to deal with the fact that I expect that this variety has some dimension, but sometimes they don't. Okay? And I would like to share with you that this fact may be relevant. And then I wrote definitions because we have seen various definitions in this workshop of tensor network, and I would just like to write down precisely. As JM said, I'm also a mathematician, I like definitions. And then to see with you in a baby example that these two definitions agrees. And then we discuss about dimension and defectiveness, and then further questions, okay? So we have heard many talks here from quantum physicists. They told us that they don't like to work in the huge ambient space where the tensor product, the huge ambient space of the whole tensor product, because it becomes quickly intractable, but they would like to have less number of parameters. They would like to find an ambient where they can work, an ambient that has some physical meaning that reduces the number of parameters. So for example, if you have your own tensor in a given basis that you don't know, maybe you know the basis, but that basis doesn't have any physical meaning, then this description doesn't tell you anything about the entanglement, right? While you know, physicists tells us that when they have particles, they like to interact if they are close to each other. But if they are very far to each other, they don't interact. And so the tensor network, they captured precisely this phenomenon, that if I have two particles close to each other, the interaction is going to happen exactly between these two particles that are close to each other. And so when I write this matrix product in these terms, I'm just saying that I have two particles. In this case, there are two qubits, meaning that they have 2 degrees of freedom. I'm looking at two informations for each one of these particles, and here is happening the entanglement. And so there is this physicist mantra that I hear in many physicist talks, that they say that the interesting states live in a corner of the Hilbert space, and that space is the same where the tensor network lives. So as a mathematician, I understand the fact that many interesting cases lives in a smaller set rather than in the whole ambient space. I'm still not very familiar with this notion of corner, because for me, when I speak about corner, there is some notion of positivity. There's some bigger or equal inequality somewhere.
It's a very bad word.
Yeah, so I would be happier if it was like, in my opinion, this tensor network is going to be a variety, and the variety is something that is like everywhere in the space. It's like a thin sheet.
It's just harder to draw in talks. I think that's why people like the corner. It's harder to draw in a talk on a slide.
Yeah, but corner may have really it may have a meaning in math, right? So I'm not. Maybe it has also the right meaning. I'm just saying that I'm not the one that is understanding why they call it corner. I would be happier with some tiny thing.
What I'm saying, it's not correct. It's because you can draw nicer pictures.
But they all call corners. So
you need to tell us how to do it right.
Anyway, so for example, matrix product states, we have seen already that they reduce a lot the number of parameters with respect to the dimension of the ambient space. They are accurate representation of physical state with limited bond length. And okay, so they're the nice place where to look for interesting states. And moreover, if physicists knows that most of the interesting states lives in this tensor network states, they know where to look when they study some objects, right? So for example, one of the big problems is computing the ground state of some certain Hamiltonian. If they know that what they are looking for is not in the whole ambient space, but it is in a smaller space, when they minimize their expectation value, looking for the minimum of this expectation value, they don't have to look in this whole space, but they can restrict themselves looking only at the tensor network, right? So especially if this ambient is very nice to parameterize, if it's very easy to approximate a tensor onto a tensor network, we have seen the first day from Roman that there are very nice algorithms to approximate very well on tensor network, right? So they are really the right place where to look. And one of the main things is that they reduce the number of parameters. So the number of parameters that I need to use when I work with tensor network it's important, right? Okay, good. So as far as we are now, I told you that the tensor network it's a tensor that where some indices get contract in dependence on some graph, right? So what I draw here, I had three-order tensors that get contract in these three indices, and I split out another three-order tensor where I have these three edges here, and I say that the tensor network variety associated to this graph with certain bond length that I've not specified yet here, only because I'm lazy, is the set of all tensor in Vn, tensor Vl, tensor Vn, for which there exists this tensor that allow to write my tensor T in this way. Okay, and since I like algebraic geometry, I like to take the Zariski closure of this set, but this is not a problem, at least for physicists, because I'm adding something that are just very close to my object. Okay, so if I'm in the closure and not inside this object, I'm really very, very, very close to I'm making like a good approximation of a tensor on the tensor network. Okay. So this is one definition, for example. But we said that we are interested in studying a parameterized object. Okay, so this definition is given by a parameterization. Okay, I have a parameterization of all of this object here. And I want to study an object that is parameterized. So, and the number of parameters is much, much, much smaller than the number of the dimension of the ambient space. But the number of parameters may be still more than what needed, right? Because every time that you have a parameterization, you have your parameter space, and you have an image of a map. The image of a map is your variety. Well, the closure is your variety. But this map may not be one-to-one. Okay, so the number of the dimension of the parameter space may be bigger than the dimension of your variety, and so
maybe some of the other physicists also don't. I don't know exactly what a variety is.
So for me, I'm thinking at an algebraic variety, and an algebraic variety is the zero set of a bunch of polynomials you give me. Okay.
So maybe you should tell them what Zariski closure is.
Yeah, but I mean, for this talk, I think it's sufficient to say that there are very close points to that, right? So a variety is just defined by a zero set of polynomials. But in this example, I mean, in our tensor network setting, I have the parameter space, I have that parameterization, right? I have this parameterization here, and it ends up in all the tensor that lies in this set here, okay? And maybe this set here is, it vanishes on a lot of polynomials, but if I look at all the polynomials that vanishes on this set, there's something more, and this something more is what I add with this closure. But I'm claiming that I'm adding something of measure 0 with respect to the measure of this thing here, and that is very close. And it's something that I can reach with a limit of points on this set. I don't know if I answer your question.
Well, it's better.
Okay. What I wanted to say is that once I have a parameterization and the number of parameter space is already something good for me, it could be that it's even better, because it may be that this map is not one-to-one. It may be that I'm still overcounting the necessary number of parameters. Okay? So I can do better. And what is the right number of parameters? The right number of parameters is the dimension of this variety. So I'm really interested in the dimension of this fiber. Okay? So if I can tell you which is the dimension of this variety, then you can reduce the number of parameters in your algorithms. Okay? Good.
Is a variety similar to what we usually think as a manifold?
Yeah, in a way you can think this. If you like it, you can think it in a manifold. I don't have any metric here, so I'm just, it's easier for me. It's just a bunch of polynomials, it's just a bunch of points defined by polynomials. But there's no metric in my talk. Okay, now I want to pass through the other definition that we have heard the first day. I'm gonna define the same object, but in a different way. So I fix a graph, for example, with some vertices and some edges. On every edge, I fix the bond dimensions, and I take the identity. So M1, M2, and M3 are the bond dimension, and I fix the identity over each edges. So the identity M1 lives in CM1, tensor CM1, the identity M2 in CM2 and CM2, and so on. And then I tensor these three identity together, okay? These three identity, where is it? I tensor the identity, so they live in the tensor space over the edges of the tensor product of CME, tensor CME. And then I think at the same object in a different reordering, so instead of taking the tensor product over the edges, I take the tensor product over the vertices. It's the same object, just reordered in a different way, okay? And I give a name to this guy. It's called the graph tensor, okay? And I call W the tensor product of the vector space that I see here. So CM1 tensor CM2 is W1, okay? So this is the graph tensor. And up to now, I've not used the physical edges. I've just used the bond dimension. The physical edges come into our story in the next slide, but you see here I put some arrows because I will look at the homomorphism from this vector spaces, the W's, out to the physical vector spaces that I see in my ambient space. And that's precisely what I'm going to do in the next slide. So I look at my graph. I have my graph tensor here. And I multilinearly multiply my graph tensor by all the homomorphism from the Wi to the Vi. Okay? We have seen this operation many times in this. So like x1, x in one direction, x2, x in another direction, and so on. Okay? So the image of this map is not yet our variety, but simply because it's not closed, I take the closure, the same closure I took before, and that's going to be our tensor network variety. Okay? So let me, sorry, I did the wrong thing. I'm going to try to convince you that this is the same definition as before in a baby example. Okay? It's not a proof. It's just, let's do this in a baby example. So I take the matrix product state with M, with this bond dimension M here. Okay? And so what did I say before? I take the identity of dimension M. There's only that one. And so IM lives in W1 tensor W2, that is CM1 tensor CM tensor CM. And then I take all the homomorphism from W1 to V1 and W2 to V2, okay? That goes into V2 tensor V2. And what do? I multilinearly multiply this homomorphism by IM, by the identity. Okay, so this is the identity matrix. I did all the calculation. This is the where is it? This is the identity matrix. This is how the multilinear multiplication acts. So x1 on the first factor and x2 on the second factor. And this is the tensor product, how I do it 2 vectors. And you see here, I have the identity inside, and I get precisely the product of these 2 matrices. And this is indeed the matrix multiplication. Okay? Good. I've not proved it for you, but it's just an exercise. So I have these 2 definitions, and I wanted to move from the one that I thought it was more known, so the parameterization to this definition, because I'm going to use this second definition. So one reason to use this is that making multilinear multiplication is just evaluation, so it's not something difficult, let's say. And evaluating the graph tensor is even easier to evaluate rather than on another tensor. And in the second item, I kind of hiding a lot of things under the carpet. So you may start saying, okay, I want to evaluate my graph tensor and hope that's what's hidden under the carpet.
So when you say evaluating, you mean perform the D-linear map?
Yeah. And being able to find those linear maps that brings your graph tensor into your given tensor T. This is a difficult problem. It's not easy because you may not able to find these guys. But anyway.
So what's the task? I have a T, and I want to find the X, and I promise they exist. But
right.
It might still be hard to find them, I see.
There are people that study that may find classes of tensor where this evaluation is easy, but it's...
So what's their definition of easy? Is it polynomial time or sub? Because
it was a naive way of use of easy. So it's easy to evaluate a tensor that is full of zeros and some ones.
Okay, it's not a computer scientist.
No, it was just... Okay, so okay, let's see some property. So first of all, we can always assume that all the bond dimensions are bigger than 1. Otherwise, I can just remove the edge from the graph. This variety has this monotonicity property. So if you have 2 tensor network variety associated to the same graph with different bond dimensions, and it happens that these bond dimensions are entry-wise, one smaller than the other one, okay, all the coefficients in one case are smaller than the coefficient in the other case, then these 2 varieties are one contained into the other one. The smallest one is contained in the biggest one. And so this reflects also the fact that in physics it's said that you can write any tensor as a tensor network. Because at some point, this guy, they fills all the ambient space. Well, not actually all the ambient space that they can fill, because sometimes it happens that this variety are degenerate. Sometimes you look them in a too huge space, and then they span a space that is smaller than the biggest one, okay? But as soon as you are in the right space, you can write any tensor in a tensor network state. Right, and so if your graph is connected, at a certain point you fill your ambient space just enlarging the bond dimensions. So another assumption that you may take is that if you have a node, and in a certain node you have one bond dimension that is huge, it's bigger than the product of all the other bond dimension incident in the same vertex and also the physical edge, then you don't need to take this M1 in this example so big. You may reduce it to be the product of all these other numbers, and you will get the same object. Okay? So this is one reduction that you can do. Other similar reduction that were introduced, one by JM, Chi, and Yi, so are not on the product of all bond dimension and one physical dimension, but if the relation between the physical dimension and the product of all the bond dimension incident in the same vertex. So they call it subcritical if the product of the bond dimension is bigger than the physical dimension, supercritical otherwise, critical if it's both subcritical and supercritical. So a first easy result on this dimension on tensor network variety is that if you are in a supercritical case, so in this case here, when one physical dimension is bigger than the product of all the bond dimension incident there, if you look at the tensor network variety, when instead of this n, you have an equality here, so you replace this physical dimension with the product of all these bond dimensions, then there's a relation between the two tensor network variety, and you know precisely which is the dimension of the biggest one, just studying the dimension of the smallest one. You just have to add this value here that is nothing else than the Grassmannian that you're just taking out when you take this vector space out. Anyway, it doesn't matter, I'm not going into the proof of this, but I'm just saying that in any of these cases, and if you're interested in dimension, you can just compute the one with the equality, and then you have also those where the physical dimension grows. I keep continuing doing the wrong thing. Yeah, this is just a consideration that studying this, the orbit of the graph tensor doesn't tell you anything about what it is in your variety out. This is a symbol that I didn't explain before. Before I said that at a certain point I have to take the closure, right? So I have the parameterization is a certain image, and then I have to take the closure if I want to have a variety. And so when I do the closure, sometimes I add some points with respect to what I had before. And so studying this orbit doesn't tell me anything about what is in the closure, right? And so there are some results that tells that if your graph doesn't have any cycle, then you don't have to do the closure because the image that you have, I mean the orbit of this graph tensor, it's already closed, okay? Otherwise, it may be non-closed. But this doesn't have anything to say about the dimension. It's just okay. So what's known about dimensions? So these people here, they computed the dimensions for this tensor network variety in the case of MPS, matrix product state with open boundary condition. And these other people here, they computed for perfect binary trees and for tensor train. Okay? I will go later on the theorem. Okay? This is what to say what it was known. It's not much, right? So what do we want to do? I said I have a map. In this case, I brought between two varieties, but we have to think that this X is the parameter space and Y is the image, our variety. And I'm interested in studying the dimension of the closure of the image. So what I have to do, I have to take the dimension of the parameter space minus the dimension of the fiber over a generic element. So I pick a generic element in the codomain, and I took the generic, and I took the fiber. Okay, and this is going to tell me something about, and this is going to tell me the dimension of this variety. So this is what I have to do. I have this map. I have the parameterization. I want to study the fiber of this map. So let's see, for example, in the matrix case, the matrix product space, what do we have? So we have seen that this graph corresponds to the matrix product, and it corresponds to look at the multilinear multiplication of the identity matrix by two matrices. Of course, if instead of taking x1 and x2, you replace x1 by x1 times some invertible matrix, and x2 by x2 times the inverse of the same invertible matrix that you had before, you will perform the same image that you had if you have x1 and x2 only, right? This is not new. This is a very well-known phenomenon from physicists. This is called the gauge group. The action of this group was called the gauge group, and this is a huge amount of elements that you have in the fiber. Okay? This is something that there is in the fiber. Good. Now, all the physicists I asked, when I said, so which is the dimension of this variety? What do you know? What do you expect? I always get this answer that they expect that the most cases are the dimension is precisely the dimension of the parameter space minus the dimension of the gauge subgroup. So here I wrote the minimum between the ambient space, it can happen that it fills the ambient space, and the dimension of the parameter space is minus the dimension of the gauge subgroup. That for sure is in the fiber, is always in the fiber. Okay? So this answer doesn't take into account two facts. One fact is that there can be something more in the fiber, not just the gauge subgroup, and also that the gauge subgroup may have some stabilizer. And then I'd have to re-add this dimension to what I take out when I compute the gauge subgroup. Okay? So, please.
So the gauge group is only matrix multiplications on the individual legs, or can it be more?
So on every edge,
Yeah.
you are allowed to multiply by invertible matrices.
Okay, and if you have more than just one identity matrix, you have a
Yeah,
product.
so I wrote it here. So it's the product over the edges of GL.
Okay, so it's defined as just this, nothing more.
Yeah.
Okay, thanks.
So a proper answer should be that the dimension of the tensor network is smaller or equal than the minimum between the dimension of the ambient space and the dimension of the parameter space minus the dimension of the gauge subgroup plus, right, the dimension of the stabilizer if there's any. And this minor or equal because there can be something more in the fiber. So on this dimension, I think it's still very wide open, the problem. So from one side, I say luckily. So there is this nice theorem of Delsken, Makam, and Walter. They say that, I mean, I didn't write the theorem. I just rephrase it in a very quick way. So this theorem is the long theorem. And they say that the stabilizer of the gauge subgroup is 0 in most cases. They write down a lot of cases where the gauge subgroup is 0. And among those cases, there are the matrix product states, there are cycles, and there are the PEPs. And these are, I mean, most of the interesting cases in physics, the matrix product state and PEPs. So if there the stabilizer is 0, I mean, we already have a lot of cases where this guy doesn't appear, so where we have to care about only if there's something more in the fiber, right? But I have to say that so we have also studied other cases, and we have, in all the cases I've studied, we have never found any example where this stabilizer is non-zero. I don't have any example where this is not 0. So I don't know, maybe it's always 0, okay? So the idea of don't taking into account that stabilizer is naively good. I don't know, but I don't have a proof. Okay, so I just simply saying that I don't have any example where this stabilizer is non-zero. So these are the theorem I announced that they were known already. So they prove that matrix product state with open boundary condition, they have the expected dimension, and this is coherent with what is written here, together with the fact that this tells us that there's nothing more in the fiber of matrix product states rather than the gauge subgroup. And the same for perfect binary trees and tensor train. Okay? So in all these cases, we know the dimension, and the dimension is that just parameter space minus the gauge subgroup. Okay? Another sharp case that we show, I forgot to say that these theorems are in collaboration with a former student of myself, is Claudia De Lazzari and Fulvio Gesmundo. So these are, this is another case where we can compute the dimension, and the dimension is the expected one, so the stabilizer is 0 and there's nothing else in the fiber, and these are the supercritical cases. Okay? I go back to the definition here. The supercritical cases are those where the dimension of the physical space is bigger or equal than the product of all the bound dimensions sitting there. So in all these cases, I have the expected dimension. Okay, so stabilizer 0 and nothing more in the fiber. Good. So I'm left with subcritical cases. What does it happen on subcritical cases? We have examples. So we did some computation. So this is a triangle with all bond dimension 2, and this is a list of physical dimensions. Okay? And we computed with upper bound, I mean expected dimension. And with lower bound, I mean that we pick a random point on this variety, and we computed the tangent space at that point, the dimension of the tangent space at that point. And we found 2 cases. We didn't compute plenty of cases, but in this example, we find these 2 cases where it is defective. These 2 cases are two, three, four, 2, 3, 4. And 2, 4, 4, 2, 4, 4. So in these cases, something is happening. Okay?
So again, the thing on the left is the dimension of the closure.
Once again?
The thing on the left is a dimension of the closure, inferred from random examples, and
Yeah.
the right one is the upper bound from parameter counting.
Right. Yeah. Yeah. So in terms of dimension, there's no difference from the dimension of the closure and the dimension of
I
the
see.
non-closed.
The closure point is not
Because
important.
when you pick a generic element, you pick something that is not necessarily in the closure, right? And when you add the closure, you're adding something that is measured 0 with respect to the rest one. So, okay. In this other table, it's a square. All the bond dimensions are again 2. And we change the physical dimensions. And so we found more examples where we have this defectiveness. This is where I say defective tensor network varieties, because I have some expected dimension, but when I go to compute the true dimension, I get some defect. I get something that is smaller than the dimension that I was expecting. And these other cases are, again, defective. So this is just a computational thing, right? So let me just write one of them. So
Do you have a geometric identification of the defect in any of these cases?
yeah, I'm going to show one in the next slide. So let's write, I don't know, let's write this one. 2, 3, 2, 3. Okay. I'm going to show you one of these cases. I'm going to show you the triangle 2, 2, 2 and 2, 3, 4, this one. Okay. So this triangle, it sits inside projective space of C2, tensor C3, tensor C4. Okay. Because these are the physical, I'm studying this case here. And I consider.
Confused, what does example even mean?
So JM asked if I have some geometrical explanation of this defectiveness, and I'm showing one example. And the example I choose is this one.
Example doesn't mean a state. When I hear example, I think of a state. No. Example just means a row here.
So
Yeah.
it's a variety. Just giving,
So
describing a
I would like to see if the dimension of the tensor network variety associated to the graph, this graph, okay, is actually equal to 22, or now it could be that, well, let's see if it's 22, okay? Now I don't remember if this is affine or projective, but anyway, we'll find the result. And I'm looking only for this case, this example. Okay, sorry for that. Okay, so this variety sits inside the projectivization of C2, tensor C3, tensor C4, and I consider, so it's a bunch of tensor living here, and I consider the flattening that flatten my tensor with respect to C2 into C3 tensor C4. So I'm taking slices, I have this order 3 tensor, and I take slices of this tensor, and I'm making a matrix of size 3 times 4 times 2. Okay? Good. This is a map that goes from C2 into C3. So the image of this map is going to be a line. Okay? It goes from C2, a projective line. Okay? A complex plane. So it's a line in here. It's a projective line in here. And so the result is that my tensor, this is just any flattening, right? If I do the flattening of, or it's a point, I mean, it could be a point, right? It's at most, sorry, let's say it again. The image of a map that goes from C2 into C3 tensor C4, it's at most a projective line. At most, it has at most affine dimension 2, projective 1, okay? But it can also be a projective point, a C1, okay? In general. If I start with a tensor that belongs to that tensor network, what it can be, I'm saying that it's either a line or it is a line that intersects the matrices of rank at most 2 in at least 2 points, counted with multiplicity. So it can also be tangent. So this is a geometric characterization of this object there. Okay?
This matrix A is in the flattening as well.
The matrix? No, this is the set. This is a set of all matrices. A is any matrices of all matrices. 3 times 4
Okay, I see.
of rank at most 2. Okay? So this is not any line. Okay? So if I start with a tensor that lies on a tensor network and I do this precise flattening has some image. And this image is special because it's, so either it's a point because it's rank 1. Okay? It's a projective point. Or it's a line, but not any line. A line that intersects this small set in at least 2 points. And so I count the dimension of this object, and this is, yeah, I wrote 21 because I'm counting the projective dimension. Here I wrote 22 because it was affine. Sorry for that. Okay, that was smaller than 23 projectively, and before it was 24. Okay? So this is a nice phenomenon, and we are...
I interpret this in terms of quantum states.
Oh, that would be fantastic if you tell me.
I just heard about it.
I'm not the physicist in this audience.
But have you tried to find such an interpretation, or you just not no physicist, so you are?
No. I really like to speak with physicists, and so in Trento we have this joint program between different departments, especially in quantum science and technologies, and I really enjoy it. So.
Yeah, no, I was just wondering, did you try to find an interpretation in terms of quantum information on states, or not really?
I've not, but I'd love
just
to.
to know if it's worth to think about it. If you already tried for a long time.
Maybe there is some funny entanglement property going on.
Exactly, that would be nice, right? That's my question. If there's some special.
So this is sort of smaller tensor network, right? Because it's the set of all matrices with rank at most 2. So this is a matrix product state with M with the bond dimension equal to 2, right? And so this line intersects this smaller tensor network, right? So let me say what we are trying to do now. How much time do I have?
About 10 minutes.
Okay. So we are still trying to work with this, now together with Fulvio Gismundo only, because my former student now she's working. She's a quantum cryptographer, and she's not studying this stuff anymore. Anyway, so we realized that this phenomenon, all these examples, there was some pattern. So for example, if you look at this, at the triangles, in all cases, we had this physical edge that was a 2, and these 2 bond dimensions that were both 2. And the same here, 2 a physical dimension here, and 2 here. Okay? And we asked ourselves if this was possibly a reason. And what we are finding, so this is a work in progress, is that if I have something like this pink arrow and something here, okay? And then I have this 2 here and here, I don't know, and 1 and 2, okay? Both cases before are in the setting. We always have the same phenomenon. So the tensor network variety associated to this specific triangle here has the same property. So I do the flattening from the C2, this V0 star is this C2 here, okay, against what's left. And I always get that the image of this flattening is a line intersecting. So this is the set of all matrices of the right size, n1 times n2, the dimension, the other 2 physical dimensions of rank at most m. Exactly as before. I had a 2 before because I had a 2 here. But now I have an m, and I get an m here. And again, if you look at this is precisely this other graph that you got here. The blue one is precisely a set of all matrices of size n1 times n2 of rank at most m. Okay? And this guy has this dimension. And the dimension, if you make the difference between what you expect and this number, you get m squared minus 1, right? M squared minus 1 is this m squared minus 1. So if you even if you have a 1 here, it works. Even if you don't have anything here, it works. It's not defective because the defect is 0, but the dimension is still the same. So what we're trying to do now is to do, okay, what is it? Because now you tell me what had happened at this point. I went to the physicist and I said, so you know, there's something more in the fiber. You can make your algorithm better because you can reduce the number of parameters. And I said, oh, wow, so how much do I gain? And I told you, well, you gain 1, 2, because the defect was this one, right? And so they said to me, so what? Should I change all my algorithms because you tell me that I'm overcounting the number of parameters of 1 or 2? And I said, okay.
That's even
Fair enough.
if you're not careful how you take out parameters, you might make the geometry of your optimization landscape worse.
Right.
And
so
it's much more concerning, actually.
Anyway, so this number is bigger than 1 if I have this bond dimension much bigger than 1, because before all examples were with 2, so I had this number, this small number. But in this case, it's bigger than 1. But what we are trying to do now is like to make this iterate. So what does it happen if I add this graph to some other graph, right? So I don't want to anticipate anything because we are really working on that. But it seems really that the phenomenon, so if you get a defect because of this kind of triangle, then you got it. So if you have this kind of triangles inside your graph, then your dimension is going to decrease. Okay.
I think an interpretation is good, right? Because my feeling is that people are much happier to fix a gauge if it serves a purpose, like to make the method more stable or so. And if you don't have a good interpretation, what you fix, it's kind of feels like you're doing something you don't.
In this case, you must have a interpretation because this is a case where the orbits are classified by Kronecker already. So you could even look on Kroneker's list and see sort of the geometry's already been worked out for you even. And because you have this basis where you have, you basically have two rank M matrices. Right? And that's what gives you your output tensor is these. You think of your output tensor as two rank M matrices, or the space spanned by those two. And yeah.
Okay.
So the invariants and everything are known. But of course, once you expand your graph a little bit, it's game over. But at least in this one particular case, it's just checking with Kroneker's table.
Yeah. Yeah. So, and the other case is, for example, the square. I draw one before, and that was. So all the other cases had this property that they have this 2, 2, 2, 2, 2, 2, and here's something, and here's something. And so it really seems that they are very much related with the same idea, right? Because these are, again, one of this thing here, and another one with this thing here, right? So, I don't know. We are working. It's a work in progress, okay? So, yeah, I have a few minutes to go. So, further questions. So, it would be nice to have a classification, right? So, are these the only defective cases? Are there more cases that are defective? And which is the best tensor network when you, so yeah, this is a question that I have. So I have my tensor and I want to know which is the best tensor network where I can, where it fits well, right? There are plenty of tensor network in the world. Physicists, they normally choose the tensor network in dependence on the problem they have, right? But is there an optimal choice, in a sense, to choose the tensor network? And so on this other question, how much the reduction of parameter can improve the efficiency of the algorithm. So we tried to do some experiment with the student, Claudia De Lazzari, as I said. It's very preliminary, so I'm just telling you what we did, but it would be interesting to continue on this. So we tried to, we said, okay, let's take an example where physicists know, so the problem is finding the ground state, okay? And let's do this in a problem where the physicists know already the answer, and they know that the answer of the ground state is on a tensor network. And then on an easy tensor network, a matrix product state is called a KLT model, on the name of the physicist that invented this model. But I mean, for this purpose, it's not important that I tell you which model is. They're looking for some ground state on some model, and they know the answer, and the answer is on a tensor network. Good. And since we deal with the reduction of the parameters, and we decided to use a global method rather than local methods, because this is really to deal with the dimension, with the geometry of the problem, okay? And so we tried to make a variation of this nonlinear conjugate gradient. And so we decided, okay, let's modify it. Let's modify it by reducing the number of parameters. It's a matrix product state, so the only reduction of number of parameters that I can do is the gauge. We know that there's nothing more in the fibers, so that's the only reduction that we can do. But let's do it, okay? Let's see how much we gain in this reduction of parameters. So we run it by the full number of parameters and the reduced number of parameters. And this is done in the line search method, that is the more expensive method, because it's the one that uses the tangent space and the gradient. So it's where you really use the dimension of your variety, where it makes the difference.
Did you do this on a finite chain or infinite
yeah,
chain?
no, on a finite chain.
I'm a bit confused. I thought this defectiveness only appears when you have loops. No? Maybe I'm missing what the goal is here.
So this is I mean, this is one case where it's not defective.
It's not defective.
Yeah.
Then what is the goal? I thought it's about
I'm just
reducing the
trying to
self-space.
understand what happens in this algorithm if I reduce the number of parameters. The gauge is always in the fiber. Okay, so I run the same algorithm without thinking of the gauge and with the gauge. Okay, just this. I mean, it was the first experiment that we did, and so we said, let's do something that we know the answer, a baby case, okay? Just a baby case, to see the difference where the parameter makes the difference. And so this is the result. So this is the comparison of the time of a single line search. And these are the comparison on the number of the line searches.
Line search means a sweep, or what?
Yeah. And this is so of one, okay? And this is all together, okay? So the comparison of the overall time to reach the end. And you see the difference is not huge, right? The difference is really small, but also the example was small, right? And so the number of parameters was not a huge number of parameters that we gained. So I wanted to show, I mean, it was just a very preliminary case. It's not, I understand it's not super huge and super interesting because it's a baby case and it's a toy case. But at least one see that it's small, but I work with small parameters and I can gain something, okay? So I'm finishing with an advertisement. So if you like this kind of problems and you have some undergraduate that is interested in doing a PhD program, we are a huge network. We got this Horizon, and we are looking for PhD students. And in Trento, we are going to open 2 positions. One in physicists, precisely on looking for this algorithm for approximating on tensor network variety, and one with me in math. That is going to be, let's say, more theoretical, but in this setting. I'm done.